Welcome, everybody, to our webinar on hierarchical modeling in sports analytics. Today's guest is a very special guest, and I think it's fair to say that none of us would be here today if it wasn't for Chris Fonnesbeck, who is the originator as well as its BDFL. So, Chris, welcome to the show.
Thanks, Thomas. Always glad to give talks for the PyMC community, and always nice to chat with you a little bit.
Indeed, yes, I've been looking forward to this.
I prefer it over beers, but what can you do?
It will have to do for now. So obviously, well, you and I go back, but you and PyMC go back even longer. So when you started this project in 2003, I wonder, did you have any idea how big it would become and whether it would still be even around like 20 years later?
No, definitely not. I made the initial version of PyMC selfishly just for me because, at the time today we're blessed with a ton of options for doing this sort of work. It's a huge ecosystem of software projects for doing Bayesian analysis. And, back then it was just, proprietary winbugs and handwritten code. So I made my own handwritten code and, tried to make it as general as possible. And then, the advent of platforms for sharing open source software code, now GitHub, but at the time, things like SourceForge, made it possible for it to get out into the wild, where, 10 years beforehand, it would have been a lot more difficult.
Yeah. And so that's looking back. I'm curious then today, how do you think the project is going? And then I guess instead of looking back 20 years, if you were allowed to dream forward into the next 20 years, where do you see we could be?
Today is great. The community is fantastic. The core of developers that we have is amazing. It's taken it far beyond my limited abilities could have done, and these sorts of collaborative things are always more successful than individual projects anyway. And PyMC is able to do some great things today, and as I'll show in a little bit, makes a lot of this stuff really, really easy. As far as the future goes, I think what we have working in our advantage is a little bit of nimbleness and flexibility that we might not have if we were, a for-profit company. Hopefully, we keep changing and adapting to new technologies, new methodologies, and taking those up and integrating them, as they become available, so that we don't, stagnate and fall behind. We see that we've done that already with our backend, moving from Theano to kind of our own flavor of Theano called PyTensor, and showed that we were able to kind of keep ourselves alive and relevant by quickly and usefully taking those things on board and making the software and the better.
Definitely wasn't all smooth sailing. And yeah, I think through all these struggles with deprecated backend and whatnot, we've really come out stronger. But it was never clear whether there would be like a solution. So fortunately, like today, I feel really good about like the whole stack and the longevity of it. But yeah, there definitely were times where it wasn't quite so certain.
No, yeah, I made it. Sorry, I made it sound very simple, but it seems like it from the outside, perhaps. But yeah, and it will not be smooth sailing, I'm sure. And it just relies on, again, having a competent team able to make sound decisions on behalf of the community, and bringing as much of the community in on board to help us make those decisions and make those changes is great too.
Yeah. So one thing that I found quite remarkable for this webinar is that it's definitely, in terms of people who have joined, thanks everyone for joining, and who have signed up, it's like one of our most favorite ones. And I thought that was interesting because I personally don't have much to do with sports analytics, but it seems to be definitely of interest to many people here. So I guess I'm curious, how much that really matches your own expectation or like your own experiences, and whether in sports analytics itself, Bayesian modeling is like really the cool new technology to solve many of these problems with.
Yeah, I mean, part of the reasons that one of the reasons that I'm here today doing this sort of work, has to do with the advent of data science and the availability of, powerful new or promising new data sources across sports, but particularly in baseball. And I'll talk about some of them in my talk. And, at sort of first pass, sort of the early days of this sort of thing, you're typically applying more kind of either sophisticated machine learning approaches or, very simple kind of linear models. Of course, the problem with that is it's limited in terms of what you can do in terms of quantifying uncertainty, building sort of really complex, flexible yet transparent models that kind of adequately account for the sources of variation that result in the observations that you put into the model. And so, having Bayesian methods available easily in off-the-shelf software like PyMC and Stan and others is really important, because we value not only, because we're using this information to make decisions, and big part of the decision-making process is figuring out how much uncertainty there is in the information and the model estimates. And so, Bayesian methods make that kind of a natural progression and a natural product of any sort of model that you're going to build there. So it's become, particularly over the last 5-10 years, it's become increasingly relevant. And we still use a lot of machine learning methods as well, and the simpler statistical models too, where appropriate. But sometimes it really helps to be able to drop in a hierarchical model or build a Gaussian process or things like that.
Well, that definitely got me very curious and excited about your talk. So without further delay, give it away.
Awesome. All right, let's see if I can get this going here. Share my screen. Here we go. Can everybody see that all right?
Yep, that's perfect.
Great. So yeah, ostensibly, as the title of the talk says, I'm going to be talking about building sports analytics models using hierarchical methods. Even deeper than that, though, it's again another opportunity for an audience that may not be familiar with them to learn not only Bayesian methods, but kind of a Bayesian workflow, and then secondarily to perhaps discover some of the latest PyMC features, because it's been evolving relatively rapidly over the last few months, and I'll use some of these methods here in the talk as well. So, going back to baseball analytics, I said sports analytics in the title. I'm going to focus on baseball here, though everything that I'm going to talk about is more broadly relevant to other sports analytics applications. But when a lot of us think about baseball analytics, the first thing that usually comes to mind is Moneyball, the book, and then the movie, and that is really where things kind of start. That really outlines more of an economic process where we're identifying assets that the Major League Baseball market had undervalued, and then you take advantage of that by taking up those prospects or these players that were previously undervalued and putting them to use at kind of a bargain basement price. But baseball analytics stretches far beyond that these days. Data science is pretty much everywhere. A lot of what we do day to day is so-called data-driven. Player evaluation, which again was sort of part of the initial Moneyball push, but we also use it for player development, getting ready for the draft, pick new players, and then even more granular stuff like in-game strategy and so on. There's a lot of data now in baseball, and almost all of it is observational. So we don't get to pick generally, at least with some limited intervention, who faces who in particular situations. So there's a lot of confounding variables, and it's difficult to kind of separate skill or lack thereof from kind of random variation. And so, Bill James, pictured here, is kind of the founding father of what we call sabermetrics, and the word sabermetrics comes from the Society of American Baseball Research. And his objective there was to look for objective knowledge about baseball. And a lot of these standard statistics that were used and placed on the back of baseball cards were just sort of counting statistics and rates that things like the number of runs scored in a season, or the number of hits, number of home runs, and so on, were typically not sufficient to account for a lot of the biases and confounders in the data. So, this is a baseball card from 1986. And these are typically the things that we would track and monitor and use for making decisions. Fast forward to 2023, and you go on a website like Baseball Savant that Major League Baseball uses as a clearinghouse for all of its data products. And you look at a description of a player now, and the sort of dashboard is very different than the back of a baseball card, right? We have things like X batting average, X slug, X WOBA. All those X's stand for expected value. So they're not even, most of these things aren't even statistics. They're expected values derived from models. And so this is kind of the end product of this sort of iterative procedure of trying to come up with kind of an objective underlying measurement of skill or capability of individual players. So, we're really what we're after here is our metrics that allow us to reliably evaluate players, or distinguish or be able to predict different baseball outcomes. Who's going to win a game? Who's going to whether a player is going to get on base or strike out, etc. And there are kind of three general qualities that we look for in a valid metric. One is we want it to be descriptive. So how well is your metric correlated with some variable of interest or observation of interest in kind of the same time period? We want it to be predictable. So how well they correlate in consecutive seasons or months, whatever the time period is. And then we want them to be reliable. So how well does the metric correlate with itself in consecutive seasons? Let's talk a little bit about the data itself. By far the most important new data product that's come out in the last several decades are those from remote sensing technologies that allow pitches and batted balls and even players to be tracked with high precision. And you can use this to answer a variety of questions. How much separation and movement are there between the pitches of a particular pitcher? Which pitcher has the largest break on his slider, things like that. And kind of the first of these technologies was something called PitchFX, which was a camera-based system that debuted in 2006. A little bit later, Major League Baseball switched to what was called the Trackman system in 2011. It actually used Doppler radar for ball tracking. And this provided really detailed data on pitch velocity, spin rate, ball flight path, ball velocity, and many other things. So this is just a picture taken from our bullpen here in Philadelphia. And then in 2020, right during the pandemic, Trackman in turn was replaced by an even better system called Hawkeye, which many of you may have seen or be familiar with from tennis, right? So when a player challenges an umpire's decision, the screen pops up with a little animated ball, and that's the output from this Hawkeye system, which is camera-based. It does a lot better than Trackman in a variety of methods of outcomes. It does a better job of estimating vertical movement. It tracks balls that are hit, into the ground or way up in the air. Tracks everything within about a 1/10 of an inch accuracy, and it completely replaced Trackman in 2020. And it consists of an array of cameras. 5 of these are record data at 100 frames per second, and that's used for pitch tracking. And then there's 7 other cameras for tracking players and batted balls at 50 frames per second. And from this, you can get, again, the spin rate of balls, the spin axis, even the components of spin, which direction that they're moving. It allows to directly measure these spin rates and axes rather than having to infer them from the observed path as previous systems like Trackman have done. Then beyond that, you can do things like pose tracking. So you can do a skeletal reconstruction rather than just kind of a point of mass with the previous, what the Trackman system did. And we'll eventually do the same thing with things like bat tracking and giving information on swing paths and mechanics and those sorts of things. The nice thing is that a lot of this data is now available to the public. The raw data is not available. It's a huge amount. It's about 7 terabytes per game. But the process data can be downloaded freely from Baseball Savant that I mentioned earlier. In addition to this, there's high-speed cameras that individual teams and players use, notably ones from Rapsodo and Edgertronic. These are really high-speed cameras. They're up to around 1,000 frames per second, and it can be used to track, tweak a pitcher or hitter's mechanics, the delivery of pitches, and this is kind of the output that you get from it. So estimates of spin efficiency, spin rate, even the pitch type can be inferred from the associated software. And then equivalently for batters, there are a lot of bat sensors available now that just attach to the base of the bat and gives you information about bat speed and attack angle and things like that. So lots and lots of data. Is it useful? Broadly speaking, yes. There's a lot of untapped potential, but there are some things that we can really utilize readily. For example, if you compare baseball outcomes to batted ball outcomes to their measured launch angle, so the vertical launch angle from which it leaves the bat, and the exit velocity, the speed with which it leaves the bat, you can see that these sorts of spatial regions appear, and we're interested as a baseball team in finding players that can generate a lot of the red and blue and green dots and avoid kind of the tan dots. So Bayesian methods then, we've got some data, we've got some metrics that we're interested in. How do we estimate those? As I said in the preamble, a lot of machine learning methods have been applied to baseball data, both in the past and currently. But Bayesian methods are particularly relevant in this context. Gives us great flexibility to quickly and iteratively build statistical models, particularly with the nice variety of available software these days. It offers a principled way of dealing with uncertainty. So we're not just interested in point metrics. We want to know, what the 90th percentile on somebody's fastball is, or the 5th percentile on somebody's fastball, etc. And with Bayesian methods, you get an entire distribution of possible outcomes and not just one expected value. And then it also allows expert information to guide the model by using informative priors that we'll see later. So we have scouts and other folks in the organization with a ton of baseball knowledge. You want to be able to integrate that into the model and alongside this tremendous trove of data that's available as well. Again, here, not surprising, we'll focus on PyMC, though you can do anything that I'm going to describe today in a variety of other packages like Stan and NumPyro. This is a project that I started a long, long time ago when I was a postdoc, is now a much larger community-based project that focuses on allowing probabilistic programming to be applied to a wide variety of settings. And it's based on what is now called PyTensor. It was derived from the Theano project a few years ago. And the important thing that it offers us as applied data scientists is that it implements what we call next generation Bayesian inference methods, notably gradient-based MCMC sampling. Tons and tons of contributors now, fantastic group that has taken the project far, far beyond its humble beginnings. So I'm not gonna kind of throw you in the deep end with a complicated baseball model. I'm gonna intentionally make this a really simple application, but sort of deceptively simple, right? So what I'm going to talk about here is estimating home run rate. So the rate which, for probability, if you like, for a given plate appearance, an individual batter will hit a home run. And again, we want to develop a predictive, descriptive, reliable metric. So we want to go beyond just counting home runs, reporting observed rates of home runs, and get something that is a little bit more useful and free of randomness and noise. So as part of this, we're going to kind of step through the Bayesian workflow, how you go from math that you write down on a piece of paper or a tablet to an encoded model, how to specify priors for your model, how to evaluate your model, and importantly, how to iteratively improve that model. So here's the data I'm going to be working with today. It's annual summarized data from individual batters. Each row is a player season. Got information about their age and their team and their position, and importantly, numbers of plate appearances, PA, and the number of home runs, and then a few other pieces of data that we'll use a little bit later. So, simplest possible model for estimating a home run rate is a binomial model, right? So a binomial model is a sum of Bernoulli trials. You can think of a plate appearance for a batter as a Bernoulli trial. You get a home run or you don't in this context. So our data generating model here is a binomial. So Y will be the number of home runs hit and will be the number of plate appearances. And what we're interested in is PI, the player's home run rate. And being a Bayesian, the critical first step is specifying a prior for anything in the model that's unknown. So this is the simplest of models, one variable, one unknown, and we're going to pretend that we're ignorant about home run rates and assign it a uniform prior. So we're saying that every probability between 0 and 1 is equally likely. Probably a bad choice. We'll revisit that in a moment, but here's what that model looks like in PyMC. Essentially, the nice thing about, I think, the PyMC API is that you got 2 lines of math, you get 2 lines of code, by and large. So P is our prior. We work down the graph from priors to likelihood. So only 2 lines here. The prior is uniform, the likelihood is binomial. And one innovation, recent innovation that I'm using here is that the shapes of these variables, the dimensions of these variables, are being specified now using coordinates, labeled coordinates. So you saw that batter column in the data set. Those are actual strings of batter names. Rather than specifying the size being, n, I'm just going to give it that dimension of unique batter names instead. And that'll come in handy later, particularly when we're generating output. All right. And so the next step in our Bayesian workflow before we run this model is to see what our model is saying before we even showed any data. So prior predictive checking is an increasingly important step. It's one that historically I have been lazy and skipped, and usually I end up regretting it because you can find a lot of problems in your model simply by simulating from it before it sees the data, and it'll kind of underline any sort of assumptions that you've made. So it's predictive in the sense that it's predicting the behavior of new data that's currently not part of the model, but it's sampling from the prior distribution, which is relatively easy. So we see big integrals here, but we actually get this really easily. So we do sample prior predictive, and we get this. So the histogram is our histogram of P's, and that's relatively uniform. I only took 1,000 samples here. And then the graph on the right is showing the blue lines is each prior predictive draw, and the black line is the actual observed data. And you see that there's quite a distance between the two. it's not a great behavior with no data. Okay, never mind. We're going to push ahead anyway, and we're going to now draw our samples. PM sample is what Thomas refers to as the magic inference button. One line we can use to generate samples. I'm going to draw 100 samples with 100 tuning steps and see what we get. And this is kind of the typical output that you see. We're using the NUT sampler, which is a gradient-based MCMC sampling method, kind of the current state of the art. And we get some warnings here. Get a little bit of feedback, which is kind of nice. And we'll dig into that in a minute. So after sampling, the next step in the Bayesian workflow is to check your model. And the first thing you want to check is, did the MCMC work? Did your fitting algorithm behave as expected? And one of the canonical methods for doing that is the R-hat statistic, which is essentially an analysis of variance that compares within chain to between chain variance. We want those to be relatively similar. You wouldn't want it, you shouldn't be able to distinguish which chain in your model that a particular sample came from. And this one, the R-hats aren't too bad for some players. For others, not so much. So we can draw a larger sample, maybe 1,000, tune the model for 1,000, and try to get rid of some of those error messages. And it's nice to do a kind of a visual check of your sample afterwards. And so this is our forest plot that plots the posterior estimates, and I've also overplotted the actual data. So these are the red dots are the observed rates of home runs. And it looks okay because all of the credible intervals include the observed data point, which is a good sign. But you can see that for some, some are far more uncertain than others, and that uncertainty is related to the number of plate appearances that we'd expect. But some are predicting, home run rates of, plausibly over 20%. And historically, the highest ever season home run rate was 15% by Barry Bonds in 2001, and he was probably cheating. An elite kind of season is sort of 8 or 9%. So having kind of an expected value of over 10 is not kind of a great estimate. And kind of identify these batters with probably incorrectly high home run rates. You can plot the ordered mean estimates and their predictive intervals, and you can see that the ones with really wide intervals are the ones with a small number of plate appearances. And this is kind of a classic issue with what we've done here, which is a no pooling model. We estimate individuals being independent from one another. How do you kind of interpret these small sample size estimates? They're probably not all elite baseball players. We can also use, we saw prior predictive sampling. We can do now posterior predictive sampling. So generate new data from our model and compare that to the observed data set. And this actually shows, even though it had a really bad prior predictive sample, it actually looks okay. The observed data looks like just another draw from our posterior predictive. So you can't judge your model completely from this, but it's a useful check. All right, so an advantage here of doing Bayesian using Bayesian models is the ability to incorporate prior information, like I mentioned at the outset. And this is relevant in baseball. We've been observing baseball for decades, more than a century, and we know a lot about it. We know particularly a lot about what home run rates should look like. And this is especially useful when data are sparse. So the trick here, the skill, the thing that kind of takes a bit of learning as a Bayesian practitioner is to choose the right functional form to encapsulate your prior information, and then choosing the right parameters that are associated with that to kind of get the shape right that you want. And there's a really useful utility function that I like to use for this that's now available in PyMC. It's called find constrained prior. And so you may know, for example, we may know that we want our distribution of home run rates to be somewhere between, say, 1% and 11% at the extremes. But how do we get that? Well, that's exactly what this is for. It just runs a little optimization. And here we're going to use the beta distribution because it's a good distribution, good flexible distribution for modeling probabilities, quantities between 0 and 1. And we give it kind of an initial guess of what its alpha and beta parameters would be. And then it returns one that satisfies the criterion, being that 95% of the density should be between 1 and 11%. So now we have this informative prior that we can use instead. If we do our prior predictive check, we can see a lot better performance even without any data, right? So we imposed information from prior knowledge, from expert knowledge, to improve our model even before we've added data to it. Okay, and we can see that, we still have extreme individuals, but they're not necessarily ones with the lowest or with the widest credible interval or the smallest sample size. We are going to get some players with high rates. But, let's continually improve this, right? At the moment, we're treating every player season as independent. That's not right? Have players over multiple seasons, and repeated measures of individuals are generally correlated. So we can improve our model to account for this. So now we're going to get into some hierarchical modeling. So what I've done so far is I've estimated an unpooled model. It means that every batter has its own parameters, probability of hitting a home run, and those individual parameters are not associated with one another. You can't learn anything from anybody else's home run rate. An improvement to this is to generate essentially a population model for home run rates. So we can say that an individual's home run rate is sampled from a notional population of home run rates that is, somewhere between 1% and 10 or 11%. And that doing that, we can share information. The way that it's shared is that we're estimating these hyperparameters, mu and sigma in this case, that are informed by all of the individuals inside the population. So you're sharing strength essentially across the population. So this population model for home run rates looks like this. It looks very similar to the unpooled model because we're using a beta distribution. But the important difference here is that we're not just sticking constant values in for alpha and beta. We're going to estimate those from data, right? So this is a population model for home run rates. Before it was just a prior. This is different. Okay, and so these HyperPriors now are things that we have to estimate. So rather than estimating our beta, we're now estimating alpha and beta, and we're going to put gamma priors on those because alpha and beta both have to be positive and they're continuous. So gamma satisfies those criteria. You can use other things as well. So here's this partial pooling model. It's got a model priors for alpha and beta, and now a model for P, not just a prior for P. Okay, and you can plot nice graphs of your model, which is also a good prior check. Make sure that all of your nodes are connected to one another in the right order. And our prior check here now is really, really quite nice. Okay. Same for the posterior fit. Doesn't actually look a whole lot different from the unpooled model. But now the massive difference we get is when we look at the estimates, the no pooling estimates on the left versus the partially pooled estimates on the right. And you can see that all of those low sample size estimates, most of which were way too high, or a lot of which were way too high, it's a player hitting a home run in 1 of 2 at bats, those sort of thing. Now they've all been shrunk down to more reasonable, believable values. There's still some extreme values in there. There's still more uncertainty in those, but we're not predicting individuals to be historically good at hitting home runs as kind of a default. Okay, let's expand our model further. We have other information in our data set that might help us predict home runs. Specifically, our populations of baseball players, like any other population, they're heterogeneous. And we have additional data that we can use to describe this heterogeneity. For example, knowing what primary position a batter plays may inform our home run estimates. If you play up the middle of the kind of middle infielder, center fielder, they tend to be smaller players. Jose Altuve, the player on the left. Corner outfielders and corner infielders tend to be larger, stronger. and tend to hit more home runs. Just so happens Jose Altuve hits a lot of home runs too, so maybe this is a bad example, but graphically, you know, you'd a priori predict Aaron Judge to hit more. So we can add this into the model as well. We can estimate, we can have different group means. So here I'm adding a random effect for based on position. So here the DIMS is position rather than batter. So there's going to be 10 total. We're not going to include pitchers here. And so we've gone from a beta, we don't see a beta anymore. Now we have this logit linear model where it's a mean plus a individual batter random effect. Okay. So our model's getting more complicated. And you can see here, these are the posterior estimates for each position. And, you know, like I suggested earlier, shortstop and second base have a smaller baseline mean. Designated hitters who are just in the game to hit, they tend to hit more home runs. And corner outfielders, first basemen tend to have higher. So you can still, we're still able to vary from this mean, but you're sort of have a more informed baseline, essentially. What about the baseball park that you play in? There is, unlike sports like soccer, there's no uniform configuration for baseball fields. Everyone can be different. As long as the length of the lines of the bases are the same, and a few other things. The distance, importantly, the distance to the outfield walls can be different, and as you might expect, that will affect home run hitting. Different parks are at different elevations. Higher elevation parks, the ball carries more further because of differences in the air density. So problem here, though, is, you know, I'm using summarized data. I don't have individual plate appearance or game data. That's what I would probably use if I was building this model for reals. But I do have information on the team that the player plays for. So the organization play a lot of games in baseball. And Major League Baseball season's 162 games. 81 of those are played at your home park. So there's a bias for each player relative to which park they're playing in. So in addition to a position effect, we can add a team effect that, you know, may encapsulate the configuration of the stadium and a bunch of other things that we won't go into here. What I'm going to use here is actually just a fixed effect, right? Because every team is playing the same amount of games. You're not really as interested in you know, shrinking small sample size estimates towards the mean. What I will use here, though, is a zero-sum normal distribution. It means that all of the team effects have to add to zero so that these can be additively included in our little inverse logit linear model down there. So there we see our thetas are now indexed by team. Okay, and so we get a sort of a sliding scale of expected home runs by team. So we've hopefully soaked up even a little more variation from our data set. We've built a bunch of models now. Just because I've created a slightly more sophisticated model in the last iteration doesn't mean that it's better than a simpler model. And it's important, another important step in our Bayesian workflow is doing model comparison. And there are a bunch of criteria that we can use to do this. We're not going to delve deeply into this here. What I'm going to use here is something called the expected log predictive density, which uses the log point-wise predictive density from the posterior distribution, or of the data, excuse me, weighted by its posterior probability of the particular model being correct. This can't be calculated, but it can be estimated, and it's estimated in a companion package to PyMC called RVs, using essentially an approximated leave one out cross-validation. And we use cross-validation all the time in machine learning to do model fitting and model evaluation. And it's a great way because it allows you to predict out of sample, and it lets every observation have its turn being the out of sample data point. The problem is that you have to fit n models generally, because you've got to fit a model with the other n-1 points only. Aki Vetri and co-authors in 2016 introduced a really neat computation of approximate LU using the MCMC samples themselves. And they're corrected using Pareto smooth importance sampling to get essentially an estimate of point-wise out-of-sample prediction accuracy. And that's what we're going to use here. All you have to know essentially is, larger value is better. And you can see that our group covariates model by a nose is better than our other two iterations. And the uninformative prior model is, as you might expect, far, far behind the others. So we'll come back to this a little bit later. A really great aspect of Bayesian modeling and hierarchical modeling specifically is it allows you to incorporate data on essentially different levels of hierarchy. So we've to date incorporated group level covariates. Well, we also have some individual covariates as well that I've included in that data set, namely some of the ones that were derived from StatCast, from Hawkeye. I've got information in here on a player's average exit velocity over the season and the player's average launch angle. And you'll see all this stuff on TV when you watch the games these days. So I can add a little linear model component here. So create a couple of betas, a couple of normal coefficients, and then just take the dot product of that with the columns of data in our data set. There comes the new model graph. And as we would expect, the home run rate is increasing as exit velocity increases, and to a lesser degree, launch angle. And sure enough, an individual covariate model is even better. These are sort of stacked on, or progressively stacked on top of each other. So the individual covariate model also includes the group covariates. So we've added quite a bit by including these individual covariates. The thing that this model doesn't incorporate, though, are some of the interactions between these individual covariates, and that can be important. Notably, launch angle launch angle and exit velocity here clearly interact. There are sort of spatial regions that are optimal, and we want to be able to identify these. So involving interactions in the model might be the next step. And one way of doing this rather easily in Bayesian and Bayesland is using Gaussian processes. And a Gaussian process is just a generalized multivariate normal distribution that's of infinite dimension. And we use statistical tricks having to do with conditioning and marginalization of multivariate normals to kind of work with this in reality. So a GP is generating functions as its realizations rather than just arrays of values. So it's parameterized by a mean function and a covariance function. And this covariance function is used to kind of describe how wiggly our function is and how it changes over time according to what the functional form of the covariance function. And this is kind of what one looks like here. This is just one in isolation. So the covariance function I'm using here is a Matern covariance function. It's very flexible and easy to implement. We've got a whole suite of covariance functions available in PyMC. And then I'm going to push that into an approximate GP called the Hilbert space GP that's really good at working with larger data sets. Because the one downside of standard GPs is they tend to be slow computationally because it involves inverting data matrices. And as your data gets large, inverting the matrix gets really, really slow. So this is what kind of a simple model looks like. We're going to combine this with using an accelerated sampling algorithm. So in the previous examples, I've been using the default PyMC backend, which is a C backend. The PyTensor library that PyMC is based on allows, its kind of key innovation is that it allows models to be compiled to different backends, not just this default C one. So here I'm going to use the NUT sampler from the NumPyro library, which is a great Bayesian modeling library in and of itself. And this uses the JAX library from Google to compile the model to XLA code, which then can be run on a GPU, which makes it quite a lot faster. In here, you can see that this model took 43 minutes to run rather than just a few seconds for the other ones. But you get a really, slick way of doing non-parametric interactive non-parametric model, essentially Bayesian non-parametric modeling. So you can see there's a sweet spot here between exit velocity on the x-axis and launch angle on the y-axis. And incorporating this GP covariate improves the model, not quite as much as in incorporating the individual covariate, but it's again adding something here. After you've got a model that you're more or less happy with, you want to use to make predictions, you want to be able to easily take that model and move from fitting mode to inference and prediction mode. And another kind of key feature to doing that is changing our data from something that's fixed to something that's mutable. So these mutable data objects that we can include in our model specification is a wrapper around a PyTensor shared variable. And what it does is it allows the values of the data to be changed later. Because all models in PyMC are these giant symbolic expressions. And when you pass raw data into your model, what you're doing is you're giving PyTensor permission to treat this data as constant and essentially optimize it away if it makes sense to do that. If you need to change your data later, you may not have any way to point at it within the largest symbolic expression. So what this mutable data does is essentially makes it an element in the graph. And so because of the structure of our model, one of our challenges is kind of a bookkeeping challenge where the prediction data will actually contain some players that weren't part of the training data, right? So if we're trying to predict into the future, we may have new players, maybe they were injured, maybe they're new to Major League Baseball, and we've got random effects that are indexed to individual players. So we need to take care that our estimated random effects are associated with the same players in the prediction data. And we can use Python set operations to kind of identify these. So we've got 34 new batters in our data set. And so now all I have to do is crack open our model and use the set data method or function, excuse me, and stick in the prediction data set for the existing batters, and then slightly expand my model by including random effects for the new batters. So I'm going to add a coordinate here for all of the new batters' index values, and then essentially have new nodes in the model just for those, because we're not going to resample our model. We're not going to refit our model. We're just going to use the samples from the fitted model before we were in prediction mode and use the mu's and the thetas and the epsilons, but we're going to draw new random effects for these players we haven't seen before. Okay, and so now our model graph is really big because it includes this whole section on new individuals that haven't been seen until it comes down to prediction. So, this allows us really quite easily to do out-of-sample prediction, sample into the future, sample with players that we haven't seen before, etc. And this, pans out rather well. So these are posterior predictive estimates for 6 of the new players, where the red line is what actually ended up happening. So this is data used through 2022 to predict into 2023, the current season. And these are all those players. And the blue line is the posterior predictive distribution. So at least for this cherry-picked example, they did reasonably well. So, just to kind of summarize our workflow steps, it's always good to do some data visualization as kind of exploratory data analysis step. Build your kind of provisional model. Don't throw everything in the model at day one. Start simple. Start with a model that previously works. Do your prior predictive checking before sampling to identify easy to find issues. Fit your model. Check your model first by assessing convergence if you're using MCMC, and then by doing posterior predictive checks to see how well the predictions from the data correspond to the observed data. And then goes this iteration, right? You improve your model, then you go back and you fit your model, reassess the convergence until you have something that, that looks kind of like the last slide in the deck. I'm going to stop here and say thanks to everybody for tuning in and following along. And I think I've left 5 or 10 minutes for questions if anybody has them. Thomas, I'll turn it back over to you.
Yes. So first of all, thank you so much for an excellent talk. It was really amazing how you really took it from like the very simple model all the way to Gaussian processes and beyond. So that's something I never managed to do. So very cool. And also, it is such a great exploration of the modern Bayesian workflow and like all the most recent features that are present in PyMC. So I think like I haven't seen everything like packaged together so nicely of like all the things we added like in the last year. So there are a whole, yeah, there are a whole bunch of questions. Some which are just like saying how amazing it was.
There's something that wasn't clear.
Right, yeah. So, okay, so one actually, which I also thought was an interesting question and something that was easy to miss. So Theo asked, could you explain the kernel function design of the GP a bit more? It looked like you were tuning the same length scale plus variance for a 2D variable. Was it spatial? And I think the background is usually when we talk about GPs, and most 90% of the GPs that people see are one-dimensional for like time series models. But this was an extension.
Yeah, that was a good catch. Yeah, I used the same length scale and output scale parameter for both dimensions because they sort of were in this particular case. You can do what's called automatic relevance determinant, ARD, and have a different set of parameters for each dimension. That's the most flexible way. It also takes longer to fit. So if you can rescale your inputs so that you only need one set, it's great to do that, but you're free to make it more flexible. In that case, you'd want to do some model checking there. And if the model displayed lack of fit, that's when you might want to go independent.
Yeah. And I also just posted a blog post on the PyMCLabs.com blog about spatial Gaussian process modeling.
Yeah, I really skimmed over the GPs. I really didn't do them justice. I really just wanted to show off an application. There is a lot of resources out there, in particular, Bill Engels, who's kind of the godfather of GPs and PyMC, has done some great work making all of these really powerful tools available to us as part of the main PyMC library. So check them out.
Another good question from Theo. What's the advantage of zero-sum normal over just normal prior with zero mean? I haven't seen this constraint forced much in other PPLs. Don't think others have such a distribution.
Yeah, it probably would work fine just with a regular normal centered at zero. It won't, the result from just a standard set of normals won't force it to be zero sum. This forces them to be exactly zero sum. That's the difference. So in many cases, it won't matter much. But if you really want to sort of hard code that, then zero sum normal is the way to do it. If you don't have to, great, because I'm sure it's more computationally efficient just to use a regular normal. But we do have zero sum constraint variables available now to us. We have ordered constraints, which is really valuable in some situations. A lot of transformations to kind of impose these design choices on your models.
Yeah, and zero sum normal is one of those other more recent additions. Yeah. And yeah, I don't think other PPLs have that. And it's really useful in many cases. I'm actually surprised that not more have it because it is very easy if you just have a set of normal priors, for example, in a linear regression, and you don't have that constraint, that there will be collinearities in there. Just because you have 1 degree of freedom too many, and that sort of gets rid of that problem in a very elegant way. And shout out to Adrian Seibold, who developed that statistical trick. Rochal asks, how would you handle the categorical variables in the individual covariate model? Does the encoding have to be done by hand, or is there a preference between dummy coding versus one-hot encoding?
Yeah, one hot is easiest. There's a pandas function that can generate dummies for you. That's usually how I do it. But your mileage may vary.
Also, there was a question whether the slides will be available. I trust they will be. There was another question whether the notebook will be available. Are you able to?
Yeah, I can make that available. Yeah, it's a little rough looking, but I can, I'm not proud.
So people can
feel
adventurous when they dive into that.
This isn't proprietary Phillies data, so I can release it into the wild.
That is actually a question I had, like all the things you built up. I mean, I know you won't be able to talk about details of the Phillies work, but maybe just as an idea, is this like in terms of complexity or something, 10% of what you would do, or is this actually representative?
For something simple like home run rate estimation, I mean, it's not secret sauce really, how you estimate a binomial rate. So, but this would be a small, pretty small component. But the whole notion of doing, projections and predictions, and some of the tools that you did see here are things that I use kind of on a daily basis, things like GPs and hierarchical models. But this was deliberately simple because I didn't want the subject matter to distract from the learning of the Bayesian methods. So.
Okay. I mean, my impression is that if that is simple, the models must be pretty crazy, because towards the end, I would not classify GPs as being simple models, but your mileage might vary. Sean Ma asks, I'm curious of Chris's thoughts on how Bayesian analytics is bringing value to his company and business when compared to frequentist regression, which is what most leadership are knowledgeable of. Is this an uphill battle when applying such complex models for business? And I mean, I think that is a really great question and something that we battle with all the time. So I guess it'll be interesting to get your perspective in terms of, I guess, more the political side or the organizational side in terms of like bringing these advanced technologies that probably many of your managers and the higher ups are not familiar with. What has been your experience there?
I think it's provided value. I mean, I think one of the underestimated or overlooked benefits of Bayesian methods is their interpretability, right? P-values are hard to interpret and misinterpreted by almost everyone, whereas probabilities are intuitive, right? If you tell somebody that there's 90% probability of something happening, or there's a 95% probability that your true values between A and B, they have a kind of an innate understanding of what that means. It's not to say that people can't misinterpret probabilities or they overstate them or what have you, or misapply them. But having our outputs in terms of probability distributions that are easy to summarize are also easy to kind of share and translate into whichever applied domain that you're using it in. In our case, communicating this to coaches and players and executives in the front office, and then I guess along with that is the robustness that comes with having kind of a global treatment of uncertainty, right? Your entire framework incorporates uncertainty at every level, and that uncertainty propagates down that graph to the observations or our predictions. And so you're not overstating your confidence in your estimates, nor are you understating them if that's the case. And so you have a relatively robust system to inform decision-making, and that has to be important.
So I obviously agree with everything you said, but nonetheless, when talking to someone maybe on the business side, do you find that those points come through and resonate, that like that the value of like this more I guess sophisticated approach is seen not just in the data science group but also outside of it?
I mean they don't really mostly care how the sausage is made in terms of whether we're using machine learning or Bayes. They see the outputs, and you need to be able to describe if you generate an output that is unintuitive or counter to what they would expect, you've got to be able to explain that. And you can introspect these models. You've got the model graph, you've got you got estimates, and you can it's kind of easy to illustrate why you're generating the outputs that you are, which again adds to the confidence. And again, they don't need to know that it's Bayesian. They don't need to know the difference between a confidence interval and a credible interval. You're just giving them something that they can interpret and have an appreciation for what we do and we do not know concerning a particular question.
Great answer. Mark Schmidt asked along similar lines, and actually something also that I'm curious about is building these models. Can you give insights in how you interact with your team? And I think he means data science team. Like, is there like a bunch of Bayesian modelers and you all collaborate on this? How does that work?
In here at the Phillies, we have a growing group of analysts, and that allows us to kind of specialize a little bit and take a little bit more time building more sophisticated models, more useful models, and alongside that are some great software engineers that work closely with us as well. So, in fact, there's kind of a gradient between the two. Most of our QAs could be software engineers and vice versa. So there's a lot of collaboration and interaction. Even though everybody has their own area of responsibility, we're all learning from one another, and the inputs from some of my models are used by others in the organization, and vice versa. So yeah, I'd describe it as highly collaborative.
And then Matt asks, do you have recommended texts for PyMC's updated syntax? Previously, I've read Bayesian methods for hackers from 2016.
Yeah, our documentation and examples go to pymc.io, and we try to keep the docs pretty up to date most of the time. The API is always up to date, and we try to keep the example notebooks up to date. You just have to check the dates on those as much as we can, at least the ones that get used most frequently. And typically when we introduce a new feature, there's an accompanying notebook that describes it and shows it in action. So that's the best way to go. There's the Ravine and Jumping and Osvaldo's book, but of course books are always a year or two out of date, but that's kind of your best go-to PyMC textbook.
I think Osvaldo's book is actually getting an update soon. There's also the Intuitive Base course, intuitivebase.com. But I would actually say the best place to stay up to date on that is our social media. So specifically in the last year, so Purna has done an amazing job always announcing the most recent changes and additions to the library. And if you follow us on Twitter or LinkedIn or Discourse, that's where you will see a post where like, hey, there's now the do operator, and here's how you use it, and here's how to better now fix the new samplers that are available. So that is also a great way to stay up to date. So Emil asks, any advice if I'm new to the field and want to improve? Thanks a lot.
So you mean the baseball field or the Bayesian analysis field?
I would assume Bayesian analysis field.
Yeah, I mean, again, lots of resources. It's always good to have, a problem, an application that you're interested in, or problem that you're interested in solving, and, using the tools to kind of achieve a concrete goal, as opposed to learning it in a vacuum. You can do it both ways, but yeah, I think you always learn faster and better if you're, and you learn kind of the ins and outs better if you're solving a real world problem that's important to you. That would be my biggest piece of advice.
Another question from Emil. Does it happen that a selected model is not really good in production? And how do you monitor and then update the model if it turns out it's not that good?
Yeah, that's constantly a problem because, the game, in my field, the game changes every year. We have different balls and we have different players, and different even rules of the game change from year to year. So we have to account for that and update our models and make them more robust to these changes. And so, yeah, happens all the time, and we're constantly having to refit models and reconfigure them. So yeah, it's an important part. It's the Bayesian workflow that I described is kind of an inner circle. There's an outer loop that's, you iterate that entire iteration when your system changes underneath you.
Yeah, that is, I guess, an area where isn't that much information yet out there for running models in production and monitoring when they stop working and all of that. So I think probably just because not that many people have gotten that far, but it's becoming more and more relevant. Jonah asks, are there applications of Bayesian inference and hierarchical models in sports betting?
Are there yeah, I'm sure there are. Folks that use them for betting probably don't want to share the models that make them lots of money, but I could be wrong. But yeah, they're used extensively for that, I'm sure of it.
A really good question from Ohio. Could you comment on the usage of Bayesian decision-making in your day-to-day applications, where you might optimize a certain decision criteria utilizing the generated posterior distributions?
Yeah, that would be the way to do it. We don't always behave that way. That'd be the optimal thing to do, right? Is use Bayes to update your, and to that end, having more than one model is often useful, right? Because you may have multiple models that perform maybe equally well or differently in different situations. You might want to update your, weights, model weights, essentially. So ensemble inference is useful, and so model weights can change in different scenarios and settings and over time. So you can use it to update that piece of the decision-making process as well. Yeah, I mean, at the very highest level, people aren't using Bayesian decision-making in this industry, but maybe we should be.
Yeah, whenever at PyMC Labs, we get to that stage where it's not just about having posteriors and analyses, but really then defining the decision-making problem and using the full Bayesian posterior to come up with the best solution and make decisions. Is where I think really the full power of the Bayesian approach can shine through. And I just posted also a blog post that's Raveen Kumar and I wrote in the chat on twiki.io. So there are a couple of more questions, but I want to be respectful of your time. Thank you so much for sharing something from the world of sports analytics with us, and looking forward to the next 20 years of building PyMC with you.
Always a pleasure, Thomas. Thanks for the invitation, and hope to see you all again soon.
Bye for now.